Welcome back to another teardown, failure analysis and hopefully repair video. The previous teardown and failure analysis and repair video didn't went so well because I couldn't find any fault with that thingy. Card here, link in the description. Hopefully this time will be different. Enjoy! What we have here on the bench is an EMAG Technologies www.emag-germany.de Emmi-12HC ultrasound cleaner, and it got built-in heating for the cleaning bath up to 85 degrees, 90 degrees. 90 degrees if it turns. No, it only goes to up to 80, so 80 degrees, but that's not too bad. We have an on-off switch. We have 3 settings for the ultrasound intensity between 50, 100 and 75%. That's a little bit odd. I would expect it 50%, 75%, 100%, but yeah, this is really old school, but it's still sold. We have here a mechanical timer which times how long the ultrasound action is actually activated. So, and you should fill up the container here before switching on. Okay, that's for the front. Nothing to see on either side. Both feature, a sturdy, not plastic, but a stainless steel handle. By the way, that's now the other side. They are really exactly the same. On the back we have more stickers with more information and most importantly power inlet. And the whole case is made out of a stainless steel that is riveted together. That's really interesting. Only a few interesting things here on the label. So the logo of the company, the address, phone numbers, everything. Of course, it's CE and recyclable and whatnot. So model, we already saw that, Emmi-12. US is ultrasound. And Leistung is power. So the ultrasound power is a maximum 120 watts. Gesamtleistung, total power, about 300 watts, and I looked at their web page, so the rest, 180 watts, is for heating. Frequency, that's the ultrasound frequency, about 40 kilohertz, and voltage, 230 volts, AC, 50 hertz. And of course, the whole thing is QS approved, and EMAG is certified as EN ISO 9001-2000, nice logo and serial number. The bottom features some ventilation slots. I mean, if we're heating there the bath with 180 watts, the heat has to go somewhere, and the heat from the electronics. 4 sturdy feet here screwed on, and a lot of screws to open the thing up from the bottom. The top features a lid, and then you have here an insert for your stuff you want to clean, and while you're cleaning you can put on the lid again, I guess. Oh, and did I mention a mechanical timer for the ultrasound? So here it's off. That is on, and it has a ding. Let's fill that thing up with some water, and I will remove this. It's just getting into the way. So a liter should be enough. Yeah, more than enough. Great. Then we connect the thing to mains AC. And now let's see what's happened if I press the main switch. Okay, lights come on, very nice. Yeah, it's a little bit unusual from the angle here, but I want to see the water bath. Let's first try, at 50%, and I switch ultrasonic on. Makes absolutely no noise. Maybe the timer works? No. If I put my finger in, no. No ultrasonic cleaning action. My finger is still dirty. Okay, so ultrasonic cleaning is out of the question. I hope this is not a mechanical failure. Let's see if we can switch on heating. Yeah, that light should come on when it heats, I guess, but it doesn't. Let's wait a while and then I tell you if the water got warmer, if it's just the light, or if there's a more serious issue with the whole thing. It's about 5 minutes later and the water is still not at 80 degrees, or it didn't heat up at all. So in conclusion, neither the heating works nor the ultrasound. That is, we haven't checked another. Oh look, now the heating is on, but still no ultrasound. The light came on. Okay, operator's error. But still no cleaning action. I thought this would be easy, but no. And I can feel the heat now coming on here. Yeah, this is not a mechanical failure of that thing, because otherwise it wouldn't ding and it wouldn't switch on the heating. So something is really wrong with just the ultrasonic part. Yeah, this shall be interesting. So let's open that thing up. Stainless steel screws, not self-tapping, real screws. At least I think so. Are they stainless? No, not quite. They're a little bit magnetic. And by the way, 2 washers and 1 washer is, one of the type that should prevent opening or accidental loosening of those screws. And we can lift that out and I can see the board. I'm not quite sure in which direction to move that. I'll give you a closer look in a second. Yeah, that's better. First look at the board. So, for your orientation, mains AC comes in here. This is just a bridge. I don't know why they use the bridge here. Probably because it carries high current and high voltage. This connection here goes down to the ultrasonic transducers. And then we have, going from mains AC in, 2 filter capacitors, I guess, fuse, and then everything is distributed. So here, this looks like the 40 kilohertz part, or at least the transformers and coils for that. 2 transformers, it seems to be something symmetric, and 2 big capacitors driven probably by these 2 MOSFETs on the big heatsink. You're asking me, how do you know that these are MOSFETs? Because I can read the labels on the PCB, and this is labeled MOS1 and that is labeled MOS2. Okay, so this is doing some high frequency, high power stuff, and this is then bridged over here into one of these transformers, probably stepping up the voltage even more. And then this goes down into the housing to the ultrasonic transducers. This little 3-pin connector here, that comes from the 175% of ultrasonic intensity with 2 ICs and a quartz. So, a quartz. 33.33 megahertz. Is that a microcontroller? It's labeled U1. Could be anything. Could be a microcontroller. And that may be an NE555. We'll see. I can't read it in that light. Anyway, we have here also a full bridge rectifier and 2 high voltage capacitors. So I guess they are rectifying mains AC and feeding that directly after it's been smoothed over the high voltage MOSFETs into that circuit. We'll see. Anyway, we have 2 voltage regulators here. 7805, yeah, it's labeled on the board, very friendly. Is 7805 for 5-volt rail and 7815 for a 15-volt rail. The 15-volt rail probably used to drive those MOSFETs here. We have another little bridge rectifier here. So with some big capacitors around it, but low voltage capacitors. So my best guess is that small transformer just gets somehow mains AC that is rectified, smoothed and regulated, and it's used to run the whatever that is and drive the MOSFETs, and the rest is really high voltage, so mains AC or above. That's just for the overview. Now let's have a look inside. So that's the mains AC connector, and these are the 2 ultrasonic transducers, these big thingies. And here at the edge you can see the heating elements which are connected to that thermostat, and it's really a thermostat. So the heating stuff is completely contained in here. It has its own fuse. Can you see that? Yeah, it has its own fuse. And that's it. I'm searching for a temperature sensor, which is probably further down and connected here. So, but the heating works, so we don't have to worry about that. We have that activity light because this is the power switch, and below it, further down here, was the selector switch for 50, 75, 100%, and this is the mechanical timer on that side, which has also an on-off function. So mains AC comes in here. And it goes into the main switch in the middle, and then it goes into the timer switch, and from there it's distributed up here. That's the connection to the board, and also directly here, these 2 red and black cables to that little thermostat that regulates the heating elements down there. But as I said, the heating obviously works. We only have to deal with the board. You remember the 3 transformers, and I was not quite sure what is doing what. Fortunately, everything, not everything, but many things are actually labeled in that thing. So is that little transformer. And it says power transformer with model number and everything. Input 230 volts, output 15 volts, 2.5 watts. So that's definitely the thing that's feeding the 5-volt rail, and I think it was a 15-volt rail. Okay, now I would like first to test that fuse here, Because, I mean, there's a fuse for a reason, and sometimes fuses just blow for no reason at all. Maybe there's absolutely nothing wrong with that thing. At least I cannot see, you know, the usual culprit, some electrolytics that splashed out their innards or are blown up, or, yeah, anything unduly blackened and burned. Yeah, the MOSFETs look all right, so that doesn't mean for sure that they're working, but yeah, no visual clues that something went wrong really with the circuitry. And since this is high power circuitry, if something goes wrong, I mean 120 watts, remember that produces 120 watts high voltage, 40 kilohertz signals for the transducers. So yeah, let's test that fuse first. So that's how a fuse should sound. Let's see how that fuse sounds. Not very good, huh? Yeah, that thing is probably blown. Let's get it out without breaking it and have a closer look. I'm not sure, but shouldn't there be a thin wire inside? Yeah, no, there is no more. Okay, it says fuse 2 amps 250 volts. Yeah, I think I have something like that. Yeah, I do have a 2 ampere fuse, but it's a T-type. So F was a fast type, and this is a, sorry, out of focus, a T-type, but it's 2 amps and 250 volts. Let's try that. I really hope it was just the fuse, because debugging that thing will be a pain in the behind, because yeah, the water container has to be filled if you don't want to damage the transducers. Okay, fuse is in, and now it sounds like heaven. Great. Let's put that back together again. And now for test. It's really hard to get a good angle here, but let's first turn off the thermostat, switch the main thing on. We are on 50% and ultrasonic. And the fuse blew. You probably could see it. Okay, yeah, nothing is that simple usually. Okay, next steps. Either reverse engineer that thing or find the circuit diagram. Let me think about that. So it was not a fuse that randomly decided to blow. Let's get that one out. Yeah, it's properly blackened. Something is drawing more than 2 amps inside here at 230 volts, so 460 watts. Quite a lot. Let's try to get the board out. Shouldn't be too hard, just 4 screws. I spoke too early. I have no idea what's the problem with that thing here. Okay. And we got that off. So I first thought they ran out of parts because, as you can see here, yeah, the construction is basically you got the bolt and then you got as a distance holder 3 nuts, and on 3 of these posts there is a plastic isolator holding everything together, but not on that post. So I thought maybe they run out of that and put one in without. But this screws in at that grounding post here. So yeah, everything's in order. I mean, this is made in Germany. And I spot another little integrated circuit or transistor, 3 pins, but that's not why we're here. Before we start measuring anything, let's put a fresh fuse in here. Okay, make sure it's switched off. Yeah, it's disconnected from mains AC anyway, but I want to disconnect it from the rest of the circuitry. Okay, I misinterpreted things. So these are 2 common mode chokes for the mains AC in, plus 1, 2, 3, 4 filter capacitors, X and Y types on the input. Oh, we'll see that in a second if I turn the board around again. Okay, so mains AC comes in here. This is ground, and between ground and mains AC there is nothing, which is good. And between live and neutral I hear something. It's not a dead short. Okay, here's the fuse holder. Then let's continue the path after the fuse holder. Yeah, not a short. Let us measure how many ohms here are on the input. And it says 1.4K. So not a short. Yeah, the first 2 filter capacitors between neutral, live and ground. Then comes our first common mode choke. And I don't expect any different results here. That's all okay. That's our last filter capacitor. What's 230 divided by 1400? Not 2. Okay, that's the bridge cable going to the other side of the board. And from there, let me rearrange things a little bit. We enter something with 4 poles. Oh, that was a full bridge rectifier. Let me just switch over on my multimeter to diode testing. So that was AC, so from here to here there should be 1 diode, and it has 0.48 volts. That's okay. And the other way around, nothing. That's good. And from here to here there should be another diode. Nothing. Oh yeah, 0.5 volts. That's good. From here to here, 0.49. And this should be isolating. Yep. And this 0.49 and 0.49 in both directions here. Okay, we have to get that bridge rectifier out and see what it's all about. I want to emphasize that the connectors here to the board are all secured, really secured, not just some hot glue. But for that connector here, that's just, yeah, without any hot glue, just in. And we got our board out and over to the bench. Okay, let's see what we can do. Sometimes it helps to put on some fresh solder, but only sometimes. Okay, 2 loose, 2 to go. Okay, that's it. Here we have it. So let's properly probe that sucker. That flattened edge here, I don't know if you can see that. That should be plus. We connect that to ground, and this should be the 1 AC in. 4.79 volts, that's okay. 4.97 volts, that's okay. We change polarity and we should have isolation. Yep. So on the diagonal we have ground, so this way around, and we have isolation, isolation, and 0.5 volts, 0.94 volts. And between plus and minus in that direction, this is AC in, sorry. That was plus, that was minus. Two diodes, 9.15 volts and isolation. And the AC inputs should be isolated either way, as long as there's no connection between those two. Yeah. Let's go back to continuity and test the mains in again. Yeah, these are the capacitors. Okay, there's nothing. Ohms. That's basically now 1.425K. That's still too much. Yeah, not enough. I've overlooked some... here. The connection over to the transformer for the low voltage rails. Let's remove that. And we should have some isolation here. Yeah, that's better. That's the capacitors charging up all the filter capacitors, and we're in the mega ohm range. Okay, and talking about that, the short could also be on that low voltage supply, but I don't believe that. So mains AC goes here. Here was our bridge rectifier. Now let's test these. 0.3 ohms. I can basically do a continuity testing here. So there's a short. The question is, what is shorting? Is it further down the line, or let's have a look. This is a transformer. Here are our two power MOSFETs. These 3 pins each. So positive goes to one MOSFET. Negative goes to the other MOSFET. That's the gate. And here, probably that's the gate. So let's try here. Okay. Okay. Yeah, that's not what you should measure on any pin of a MOSFET. Question is it the MOSFETs? Who knows? More soldering, huh? Yeah. So, here are the pins of the MOSFETs. They are still screwed on the heatsink. I mean, I'm pretty sure they are shut, but I don't want to take any chances. Some fresh solder always helps. That's the brunt of it. Let's remove now the screws holding them to the heatsink. The first one is almost loose. Almost. Oh, that's an important part. So they were isolated from the heatsink. That one is still a little bit sticky. Okay, got that one too. So these are both RF840s. And that's the circuit diagram, or at least a part of it, I was talking about, but it's for a larger model. But it's, I think, basically the same circuit. You have that little microprocessor here with the quartz. Where is it? Here. That's a quartz. That's not a quartz symbol, but it's a quartz. And that was a little semiconductor at the back. It seems to be a power on reset circuit or something. That's the smaller package on the front. That's a high-low MOSFET driver. And here are the two MOSFETs. Rectified mains AC comes in here, and down here is ground. So they were basically a half bridge driving one of those big transformers. And if one would go, then the other one would basically short too. So if that is shorted and that is switched on, it gets directly mains AC down to ground, or vice versa. So basically the short I measured before should be gone now. So let's test that theory. Okay, AC in here, DC out here. Just making sure that I really get contact. Yep. Let's see what the resistance is now. Oh yeah, there are a lot of capacitors, so this value is rising. But 500K, that sounds about right. Yeah, perfect. I've marked out the tracks a little bit. So this is the ground output from our bridge rectifier. And that goes here to the one MOSFET. And then we have here the positive output of the bridge rectifier. And this goes here to that pin of the MOSFET. And these are basically the two center pins of the MOSFET. Here is just a wire bridge on the other side. And that leads to one leg of the transformer. And then from the transformer, the other side of the winding, it goes back via two capacitors here and here to the positive rail and the ground rail. Now, if I measure between that pin of the MOSFET and positive, we should get something high, which is slowly dropping and rising again. Yeah, because this is coupled via a capacitor. Okay, and to ground we have probably the same. Okay, rising. Obviously, that part here of the circuit driven by the two MOSFETs, it works fine. And this C17, that does not exist on our board. I don't know about these, this is probably some suppression circuitry here when the MOSFETs are switching that big inductivity that is the transformer, but these two are in place. So one theory, I mentioned it again, one MOSFET gave up and shorted out and then the other followed, or the other way around. The question is, we measured between the gate, the source and the drain also basically a short or very low resistance, and we have mains AC coming in here, so that might have fed back somehow here into our driver circuitry for the MOSFETs and destroyed something there. So this chip here, which could have been destroyed, is a reference to ground. And of course the diodes here could have died too. So we should measure the gate pins to ground and see if this is a reasonably high resistance. Should be. So, 1 gate pin to ground. Yeah, mega ohm range, some capacitors charging up, looks good. That gate pin to ground. 553 ohms. That's not good. On second thought, that's perfect, because you see here from the gate we have one 560 ohm resistor going to ground. So yeah, that's also okay. I'm still not convinced that the low voltage driver here survived. So I guess we have to whip out the oscilloscope and see if we can measure some signals here driving the gates. Yeah, the only problem I see here, the microcontroller controlling all that gets a synchronization pulse here from that second transformer. So I'm not quite sure if the whole circuit will run without the high voltage side being energized and generating that synchronization pulses. But when you start up the whole thing, before you get your first synchronization pulse, you have to switch the transformer to create something that can make a synchronization pulse. And so I think we should see something on the oscilloscope here at the gates, even with the bridge rectifier removed and no voltage here coming in. What I want to do is measure these two gates here with the oscilloscope without feeding mains AC, rectified mains AC in here, and see if we still get here pulses or control signals to the gates of the MOSFETs. I hooked up the mains AC input of the board to my isolation transformer, card here, link in the description, and the oscilloscope is already in the background, and I also soldered some hookup wires to the board, so I have ground and the gates of the two MOSFETs here. Let's switch on without the oscilloscope and see what happens. Okay, we are drawing 0.06 amps, about 2 watts. So that seems okay. Now I hooked up the oscilloscope probes too, so we have 50 volts per division, just in the beginning to be safe, and 10 microseconds per division. Now, there's something happening here. But we have to change our scales. So one of the MOSFETs gets a nice drive signal here. Yeah, about 50 kilohertz, and in the amplitude 10 volts measured to ground. Don't get a clear signal here. Question is why? And the answer is obvious. I should have thought about that before. The one gate here, which we see a nice signal, is actually referenced to ground, but the other gate in a half bridge is obviously not referenced to ground, but to the middle point. So let me try to connect my oscilloscope ground here and then measure the other signal. I got my oscilloscope ground now connected to one pin of the transformer, so the middle point of our half bridge. And as you can see, that second MOSFET doesn't get any signal. Oh, yeah, the driver is trying to do something, but yeah, that's not enough compared to the other MOSFET gate. So we know that this MOSFET gets a nice 10 volt square wave in, which is perfect, and that comes from our MOSFET driver, which in turn is controlled by the microcontroller. And obviously it still gets a 50 kilohertz signal here. So this part is working. However, That MOSFET driver also contains a little charge pump here to get the gate drive voltage for that MOSFET, and what's coming out here at that pin is it's 50 kilohertz, but it's some noise. So that diode could be shorted, or that diode, that's a zener. So these two limit the voltage at the gate. Then this resistor could have a problem, and this resistor could have a problem, and this capacitor and this diode could have a problem, or the MOSFET driver here could have a problem. Oh, that's a lot of possible problems. Oh, let's start measuring. Okay, so that is one of the diodes protecting our gate from overvoltage, and yeah, 5.66 volts in that direction. That is okay. And absolutely nothing in that direction. That seems fine. Let's go for the zener. 0.638, maybe that was conductive direction. Yeah, so they are both okay. The resistors, there's one parallel R2. This is this one. That should be 560 ohms. Yeah, looks good. And the other one in series should be at 33 ohms. Yeah, looks also fine. And then we have the rectifier diode. This is that one here. Not rectifier, yeah, kind of rectifier. That's the diode from the charge pump. 0.5 volts. Looks also good. The other way around. Okay, nothing and nothing. Seems also fine. That leaves us with the chip itself and the capacitor. So I measured around a little bit more, including that 100 microfarad capacitor, and the passives here seem all to be okay, but the culprit is probably that IR2184 MOSFET gate driver. It didn't survive that event. That's it for today. Now I have to go shopping for IR2184 MOSFET driver. I hope this is still available. 2 IRF840 MOSFETs, and just to be on the safe side, I will also order it was labeled R8PC1010 full bridge rectifier. I mean, it measured out okay, but when the 2 MOSFET failed, a lot of current was going through that thing. So I don't trust it anymore. Anyway, it will be a while until I get the parts, if I can source them. Till then, bye.